interval of integration is infinite. And the second type of integral here is, the bound of the integral in this case are real numbers, but at some point in the interval of integration, the function is discontinuous. Okay. And for both cases, you guys have improper integral, and later on we'll see how to calculate such integral. And here are two examples. The first one here, we integrate from 2 to positive infinity. Because of the of positive infinity, that's why we have improper integral of type 1, and that's exactly what I mentioned here, and I call the first case. Okay, so this situation here where the interval of integration is infinite is right here, because we're going from 2 to positive, so it means the width of this interval is infinite. Okay, this is the first type of improper integral. And the second one is when you guys have integral with where the bounds are real numbers, but at some point we have discontinuity, and that's exactly what I'm going to show you here. So this is an improper integral of type 2. As you can see, the bounds of the integrals are real numbers, different to the first example. But at the point 2, you guys can see the function is not defined, because when you substitute x by 1, you see here you'll get 1 over 0. And in this case, the function is undefined. And if the function is undefined, it's going to be for sure discontinuous. Okay, and this is the situation that I call improper integral of type 2. And the discontinuity, as I mentioned before, could be the endpoint, as this example. It could be the other endpoint. For example, it was here x minus 4. In this case, the 4 going to be the point of discontinuity. And it could be also a point between 1 and 4. Doesn't matter where is the point, as soon as your point is somewhere in the domain, in the range of the integral. So you have an improper integral of type 2. So later we'll see how to calculate each of these kind of integral. Okay, so first of all, we were going to focus on this first type of improper integral, and I'm going to give you 3 situations. Okay, because I told you for improper integral of type 1, the interval of integration is infinite. It means the width of your of the interval of integration is infinite. And this happened in 3 situations. First situation is, for example, here, if we integrate from a number a to positive infinity, or if we integrate from negative infinity to a number b, or when we integrate from negative infinity to positive infinity. In these 3 situations, we have improper integral of type 1, because we have at least one of the bound of the integral which is equal to positive or negative infinity. And as I mentioned before, as soon as you guys notice one of the bound is equal to positive or negative infinity, you have improper integral of type 1. And now we will see how to calculate each of these improper integral. In the first case, what the technique says, or the term is, you remove infinity. The reason is you cannot say I'm going to calculate, I'm going to use the FTC and calculate f at infinity. It doesn't make sense, because you cannot reach infinity. So you cannot calculate the value taken by a function at infinity. You can calculate the limit when we are going to infinity, because you cannot reach it. Okay, so be careful. If you guys write f at infinity, it means you don't know exactly what you're doing and you will be penalized. Don't write it. Okay, don't say I'm going to calculate the antiderivative at a and the antiderivative at infinity and subtract as the FTC says. No, FTC says you apply that formula when you manipulate real numbers, but infinity is not a real number. That's why you cannot do it. And in this case, what you have to do is to remove infinity and replace it by a parameter t. You calculate your integral in terms of t only. And when you get it, now you calculate the limit when t is going to infinity. So it means in the first step, you have to write down this formula, and then second step, you calculate separately this integral. And when you get it in terms of t, now you calculate the limit, the last step, you calculate the limit when t is going to positive infinity, and the value of your limit going to be the value of your integral. Yeah, go ahead. T is, you see, it's changing, it's going to infinity, it's not fixed. No, you don't take a number, because you take a number, you cannot say the number, you cannot say I'm going to take a 2, and after you say 2 is going to infinity. 2 is constant, it's not moving. You know what I mean? So just say t, and then after your integral going to be in terms of t when you calculate it, and you let your t going to infinity. Okay. So t, is like a variable, but we could just call it a parameter. In the second case, we want to integrate from negative infinity to b. In this case, you remove infinity and you just replace it by t. And as I mentioned before, t is not a constant. Okay, it's taking values, it's changing. Okay, you calculate it, and your integral gonna be in terms of t, and after that you let your t going to minus infinity, and the value of this limit is equal to this integral. So sometimes this limit gonna be a number. It could be also just infinity plus or negative infinity, depends on the situation. And for the last case, so we have to integrate from negative infinity to positive infinity. First of all, you're going to split it into integrals. You guys can see here is integral from negative infinity to positive infinity. And then you split it into integral from negative infinity to a real number b, any real number b, which is a constant. You can say from minus infinity to 0, or from negative infinity to 5. Okay, or from negative infinity to negative 7, plus now from b to positive infinity. And you notice now, by doing so, you guys will get two improper integrals. So the first one here is an improper integral similar to example number 2. So here the second situation, and the second integral here is similar to the first case. And you apply exactly what I said for the first and the second case, and that's exactly what you have here. This is similar to the second case. As you can see, t is approaching to minus infinity. So since I have two integral, that's why I use t1 and t2. Okay, I can use something else. I can use k and l. Doesn't matter how you name your parameter. Okay, so here, since we have only one integral, that's what I call t. In this case, we have two integrals. I use t1 to calculate the first integral and t2 for an integral, and obtain from these subdivision here that I did to split my integral into two integrals. Okay. So next we'll see an example, some examples, and see how to apply, what the term says here. All good? All right. In the first example, we just want to integrate from 1 to positive infinity, x times e to the power negative x. As I told you, you guys have here the interval is infinite because we're going from 1 to infinity. It's infinite integral, so that's why it's going to be improper integral of type 1. So we're going to apply exactly what the rule says. All right. So you guys can see I just remove the infinity and replace it by t. And after that, I'm going to let t going to infinity. It's going to be exactly the same value. Now, as I told you, you're gonna calculate your integral first in terms of t, and when you get it, you let t approaching to infinity. So I'm just focusing on the integral, and I'm gonna apply the limit later when I get my integral. Okay, so let's evaluate the integral here, and you notice here this the integrand is a product of two functions, so we can try to see if it's possible to use integration by parts since we have the product of two functions. Okay, and to do so, I'm gonna set u equal to x and dv equal to e to the power negative x dx. I'm gonna calculate du and v. So du in this case setting u equal to x, in this case du gonna be dx. And if dv equal to the power negative x, the antiderivative gonna be negative e to the power negative x. And then I'm gonna apply, you know, the formula is gonna be uv gonna be minus x times e to the power negative x. You take it at 1 and at t, as the FTC says, minus integral of v du. That's what the formula says. V du gonna be negative e to the power negative x times dx. This is my v du. Now for the first term here, I'm gonna calculate it as the FTC says. I'm gonna substitute x by t. I'll get the first term here. With this minus sign, I took it out. The minus is in front of the bracket. And minus a power negative x is negative e to the power negative. With this negative sign, it becomes a positive. And I just copy, you know, open this bracket and put this minus sign inside. It becomes minus t e to the power negative t, and these two minus sign becomes plus e to the power minus 1. But e to the power minus 1 is equal to 1 over e. And from the second part here, so I calculate e to the power minus t minus e to the power minus 1. With this minus sign, that will get here minus and plus. And this is exactly equal to this integral, because that's exactly what we calculate here. This integral here, this, we're gonna replace it here in order to find the limit, because it's right here. Is it okay? So next we have to replace you know, the integral here by its value, because we already calculated. We put it back here and let now t going to infinity. And you guys can see when you do so, you calculate the limit of the first term, you will get an indefinite integral, indeterminate form, sorry. So we'll get here indeterminate form, because you can see when t is going to positive infinity, so e to the power negative t is going to 0. So we'll get here minus infinity times 0, which is indeterminate form. The second term does not contain any t, constant, it's a 1 over e. The third term is going to 0, and the last term is also constant. It means we only have a problem with the first term because of the indeterminate form. Second term is a constant, the third term is going to 0, and the last one is a constant too. Now we're gonna calculate this. When we calculate it, so we come back here and substitute by its value. We just want to calculate the limit of the first term. Now, when I calculate the limit of the first term, I told you we'll get here infinity times 0, which is an indeterminate form. And I notice here the exponent of e is negative. Not negative, but we have a negative sign. So I'm going to bring it down in order to make it positive. Okay, so when you bring it down, it becomes t over e to the power t. And when t is going to infinity, so you guys can see here, we'll get infinity over infinity, another indeterminate form. But based on, you know, our first chapter, when you guys have infinity over infinity, so it means you have the right to use the L'Hopital's rule. And that's what I did. Just keep in mind, I'm just calculating the limit of the first term, because the other terms, you know, are easy to get their limits. But the first term is a little bit complicated because of the presence of the indeterminate form. That's why I'm just focusing on the first term then. And when I get it, I'm going to, you know, go back to this step and then calculate the limit. So when I apply the L'Hopital's rule, you differentiate the top and the bottom, and you will get to just 1 over et. And you guys can see when t is going to infinity, the denominator is going to infinity, and 1 over infinity is going to be 0. So basically it means, in fact, the first term here is going to 0. The second term is constant. The third term is going to 0. The last term is constant. And that's exactly what I calculate here. So back to here, I just replace, you know, this with its value right here, because it's my integral. And by doing so, I'll exactly this. Right? And I already proved the first term is going to 0. The second term is a constant. The third term is going to 0. Last term is a constant. So it means when you let t going to infinity, so this bracket is going to 1 over e plus 1 over e is going to be 2 over e. And you're done. The value of your improper integral. Any question regarding the first example? You all good? Any question?
No, sir.
All right.
No, sir.
So, yeah. Okay, let's move on. All right, so example number 2. All right, so example number 2, we want to integrate from negative infinity to positive infinity, 1 over 1 plus x u squared. So since here you have, we're going to integrate from negative infinity, as I explained at the beginning. I'm going to split it into integrals, okay? I'm going to write as integral from negative infinity to any other number. Okay, I can say from negative to 1 or 3 to 7 minus 10 minus 100. I'm just going to choose 0. 1 over 1 plus x u squared plus now the integral from 0 to positive infinity of 1 over 1 plus x squared. And as I mentioned before, you guys can see you have two are improper integrals of type 1. Okay, and then we can apply exactly what I did for the first example. Okay, now let's see. Okay, I'm going to give you 30 more seconds to write down this step. Okay. All right, so that's what I did here. I split it into integrals, integrating from negative infinity to 0, and from 0 to positive infinity. And from the first improper integral, as I told you, you remove the negative infinity and you replace it by a parameter. In this case, I'm going to name it T1 instead of T. And as I told you before, the reason is just I have two integrals. I don't want to confuse you. That's why I just want to use two different parameters. I don't want to use the same parameter for two different integral, so it could be confusing because one is going to minus infinity, the other one is going to positive infinity, so that's why I cannot take the same T. Okay, and so we as I mentioned, negative infinity, and we replace it by T1, and in order to get the same thing, so the T1 should be going to minus infinity. That's what I mentioned. From the second integral, again, this is similar to number one that we did. You remove positive infinity, replace it by T, but you let your T going to positive infinity. So we know here's the antiderivative of this function is tan inverse. So that's why we got tan inverse at T1 and at 0. Similar for this one too. Okay, tan inverse of 0 is equal to 0, and tan inverse at T1 gonna be exactly the second term. From one integral here, gonna be tan inverse at T2, as the FTC says, minus tan inverse of 0, but tan inverse at 0 is equal to 0. And now when we let T1 approaching to negative infinity based on how the tan inverse were created, if you guys remember second chapter that we did at the beginning of the semester, okay, how the tan inverse was created. So it means when you let T1 approaching to minus infinity, the tan inverse is going to negative pi by 2. It's similar to ask yourself which tan gonna give us minus infinity. As you know, it's gonna be pi by 2 minus pi by 2, because if you calculate the tan inverse of pi by minus pi by 2 is gonna be sine of minus pi by 2, which is equal to minus 1 over 0 cosine of pi by 2, and we'll get minus infinity. That's the only reason. So here it means tan inverse at minus infinity is equal to negative pi by 2, and tan inverse at positive infinity gonna be pi by 2. And then when you drop the brackets, you have two negative signs here, it becomes a positive pi by 2 plus pi by 2, and the solution is gonna be pi. Yeah, go ahead. We integrate this to get tan inverse. It's already integrated from this step to here. Welcome. So you know the derivative of tan inverse is equal to 1 over 1 plus x squared, and we prove it at the beginning of the semester how to get the derivative of tan inverse. Any question? All right. All right, so let's move on to the next example here. Now we have an integral which depend on a number p, and we would like to know. I'm just going to give you the what do you mean? What is the meaning of convergent before talking about this integral, because so maybe you don't know exactly what is it. I'm going to give you first I'm going to give you just one definition here. Okay, an improper integral is said convergent if its value is a real number. Like our two examples here. Here we got 1 over e, 2 over e. Here also we got pi, and for both of them we have a real number, so we can conclude this integral is convergent. So an improper integral is said convergent. Oh, so again, convergent if its value is a real number. Otherwise, the integral is a divergent. So if the integral is not convergent, we conclude the integral is divergent. Okay. So to be convergent, the integral should be equal to a number. Otherwise, if it's not equal to a number, your integral is divergent. So not equal to a number, it could be minus infinity or positive infinity. In both cases, your integral is divergent. Okay. So for example, here when we calculate, we got 2 over e. So this integral is convergent because its value is equal to a number. For the second one, same thing, because when we calculated, we got pi. And for both integral, so you guys have an improper integral which is convergent. Oh, okay. I wrote here improper. The word integral is missing here. Improper integral. Okay. All right, so keep in mind, to be convergent, the improper integral should be or should have a value, which is a number. Otherwise, your improper integral is divergent. Is that okay? I said an improper integral is set convergent if its value is a number. Like these two integrals, when we calculate their values, we got a number. In this case, we conclude the two integrals are convergent. Is it okay? If now your integral is not equal to a number, you conclude your integral is divergent. Sounds good? All right.
Sir, can you go back to the example 1? I haven't knocked the feed.
Pardon?
Can you come back to example 1? I just finished my check note.
I took PowerPoint or my notes?
Your note, example 1.
Okay, so we'll see it after. Okay, if I ask you if you're done, let me know. If you're not done, let me know. I'm gonna let you write down. Are you done?
Not yet, sir. Just one. Yeah, thank you.
All right, so next example.
Sir, so both 1 and 2 are convergent integrals.
Yep.
So can you give an example of a divergent?
So we'll see it later.
Okay, thank you.
Divergent means if you don't get a number, okay? If you calculate it and get infinity, it's gonna be divergent.
So what do you mean by not getting a number?
If you calculate your integral and don't get a real number, infinity is not a number. Okay?
Okay, sir. So
Yeah.
if I get infinity, then it's a divergent.
Yep.
Okay, thank you, sir.
Infinity is not a number. Okay? It does not belong to the set of real numbers. If after calculating your integral, you get a real number, you conclude your integral is convergent. If you get infinity, plus or minus infinity, if the limits, does not exist, your integral is divergent. You have three situations where you conclude your integral is divergent. The limit does not exist, or the limit equal to positive infinity, or the limit equal to negative infinity. In these three cases, your integral is divergent. Otherwise, it's going to be always convergent. Okay? Sounds good?
Yes, sir.
All right. So next we'll see an example where the integral is divergent. And just keep in mind the definition here, and we'll see it in this next case. So in this example, the question is to find all values of P, making this integral convergent. In other words, it means find the values of P for which the value of this integral equal to a real number. Okay, is it P equal to 2 or equal to 3 or P equal to -7? That's the question. For which value of P the integral is convergent. Okay, and to solve it, we're going to use exactly what the previous term says. And as I said, keep in mind convergent mean when you calculate this, you're supposed to get a number, not infinity. All right. So here is our example. We integrate from 1 to positive infinity, 1 over x to the power p when p is any number. We just want to discuss about the values of p making this integral convergent. And to do so, I'm going to calculate the integral first. And as I told you, remove infinity and you replace it by t, and you let your t going to infinity. And this integral, I'm going to write it as a power function in order to be able to use a power rule. And to do so, I'm going to take this denominator and send it to the top. And by my exponents become negative p, as you know. Example, when I have x 1 over x, you square it. If I send it to the top, it becomes x to the power -2. That's the meaning of this writing. That's exactly what I use. Is it okay? Now I'm going to use the power rule. And what the power rule says is if you guys integrate x to the power n, no matter what is n, the integral, we know we did it, I guess 2 or 3 weeks ago, n going to be x to the power n plus 1 over n plus 1. This is our rule for the integral, plus now the constant c. Now I have my n equal to minus p. This is my n. I'm going to apply this formula when n is by minus p. And by doing so, you guys will get x to the power n plus 1 over n plus 1 because my n is minus p. And we use exactly what the FTC says. You integrate from 1 to t. That's why you're going to be here at 1 and at t. Provided that now p is not equal to 1, because if p equal to 1, you cannot say the integral is equal to this, because when p equal to 1, you see the denominator is going to be 0, and we cannot divide by 0. That's why we have to add this condition here. And later, we will see this case, because we are, discussing about the old situation for p. P cannot be 1, and we'll see later what's going to happen when p equal to 1. Okay? Now I'm going to calculate this by using exactly what I mentioned here. Is it okay up to here for all of you guys? If you have questions, this is the right time. I don't want to go to the next page and after come back here. If there is something which is not clear, so let me know.
Can you go again by the power of minus p?
I just use this formula. N is equal minus p. When you integrate here, integral of x to the power 3, you know this is equal to x to the power 4 over 4. By using this power rule, n equal to 3. Same if you calculate integral of x to the power -2 now is going to be you apply the same formula when n equal to -2. It becomes x to the power, you substitute here n by -2 is going to be -1 over -1. Because in this example that I'm doing, my n equal to -2. So you substitute going to be -2 plus 1, gonna be -1. -2 plus 1, gonna be -1 here. And this becomes -1 over x. We just apply this rule. In my example, the p is my n. Okay, so you apply the same formula and you replace your p here, your n here, you replace it by -p. That's exactly what I did. So we've seen this this formula a couple of weeks ago. Is it okay?
Yeah.
N equal to -p, that's why you have -p plus 1. Your -p plus 1. The whole thing, the minus sign and the p are your n. Is it okay? All right, so next step, I'm gonna calculate this at t. As the FTC says, I'm gonna replace x by t. It becomes a t to the power -p plus 1 over -p plus 1. And next, I'm gonna substitute x by 1. So you got 1 to the power -p plus 1 still equal to 1 over -p plus 1. And now we're ready to calculate this limit. Is it okay? All right. To calculate this limit, it depends on, we have to take into account, the exponent, because depending on the sign of this exponent, the result will be different. Okay, I'm just gonna give you quickly an example. Let's say you guys want to calculate the limit of x to the power 3 when x is going to positive infinity. Okay, and the limit of x to the power -3 when x is going to infinity. You guys can see the difference between these two limits. Both of them are going to, for both of them, x is going to positive infinity. The only difference is the sign of the. For the first case, what is the limit in this case? What is the limit of x cubed when x is going to positive infinity?
So indeterminate form?
No. If you have 100,000 billions to the power 3, it's going to be 100,000 billions times 100,000 billions times 100,000 billions. It's going to be a big number. So it means it's going to positive infinity. What about the second one here?
0.
0 exactly. You see, what makes the difference here is your negative sign. Because of the negative sign, the limit changes. Why it's 0? Because this is exactly equal to the limit of 1 over x to the power 3. It's the same thing. When you bring it down, because the exponent is negative, you bring it down, and x is going to infinity. You will get just 1 over infinity. That's why it becomes 0. Example here is, if the to infinity, the second term here does not change because it does not depend on t. No matter what t does, this is still equal to the same thing. Okay, the problem is the first term, and depending on the sign of the exponent, you will not get the same result. When the exponent here is positive, as I said, the limit going to be infinity. And when the exponent is negative, the limit going to be 0. And that's exactly what we're going to apply here. When we calculate this limit, we have two possibilities depending on the sign of the exponent. That's what we observe from our previous example. You see here, when the exponent is positive, as I told you in the example of x cubed, exponent positive, it means this is going to positive infinity. But positive infinity divided by p minus p plus 1 still equal to positive infinity, minus this number, because this is a constant, p is a constant, this is going to be just infinity. That's why we get positive infinity if the exponent is positive. Now, if the exponent is negative, less than 0, this is going to be 0, as we observe for x to the power negative 3. So if this is 0, it means the whole bracket is going to 0 minus this term. That's why we got this value, obtained from 0 minus 1 over negative p plus 1. And it means we have the same thing. I just want to change here the writing of this of these two conditions, because the problem was to find the values of p, making this integral convergent. But I don't have here the values of p. What I have the values of p plus 1. So I'm gonna rearrange this. I'm gonna take the minus p and send it here to the right. It becomes the minus p less than 1. So it means as soon as minus p is 1, my integral gonna be equal to positive infinity. And in this case, the integral gonna be divergent, as I told you before, because for any integral for which the value is equal to infinity, it's an integral which is divergent. And for the second condition here, I'm just gonna send my negative p to the right. It becomes a p greater than 1. So when p is greater than 1, the integral is equal to this number, and this number is not infinity, it's a number. Greater than 1 and less than 1, because I told you here p is not equal to 1. Now we're gonna see next what's gonna happen when p equal to 1. Is gonna be divergent or convergent. Is it okay? Before we'll see, we check, the last case. Any question? Can I move to the next page? Now, guys, move to the next page. Yes or no?
Yes, sir.
Yes.
Yes, sir.
Okay. All right. Thank you. So next we will see the last situation here. From this that I call star, it's a divergent, my integral, if p is less than 1, and it's convergent when p is greater than 1. Now the question is, what about p equal to 1? That's what we will see. Now, if p equal to 1, your integral becomes, you replace here your p by 1. You see here? The integral is 1 over x to the power p. When p equal to 1, you replace p by 1, and the integral becomes 1 over x only, right? And that's exactly what, that's exactly what we have here. So if p is equal to 1, our improper integral becomes only 1 over p, 1 over x, because the p is 1. And then we apply again the term technique to calculate the integral. Is going to be the limit when t is going to infinity of 1 over t, from 1 to t of 1 over x. So, and 1 over x we know is the antiderivative of ln of is the derivative of ln of absolute value of x. So we take it at 1 and at t. So at t we get here ln of t, and at 1 we know ln of 1 is 0. And now when you let t going to infinity, the log function here is also going to infinity. What we can conclude is, if p equal to 1, the integral going to be infinity. So it means the integral going to be divergent. For the guy who was asking about an example where we can divergent, you guys can see it here. When you integrate this function 1 over x, after calculation you get infinity. It means, since you get infinity, it means this integral is divergent. Now combining this case, which is p equal to 1, and the previous cases, we can conclude about p. So from and is going to be convergent is greater than 1. And that's exactly what we combine. We combine star the previous result and double star this one. It means this integral is convergent if p is a number which is greater than 1. Otherwise, it's going to be divergent. Convergent if p is less or equal to 1 is going to be divergent. And that's what we prove here. Any question? And from what we prove here, I'm just going to generalize it, because this is not only true for 1. It's true no matter what is the value. As soon as it's a positive here, from positive number to infinity, we'll get the same conclusion here. Okay, that's what I want to just write down here. You guys can. As a theorem, and it's called the p-test. I'm going to call it first P test because I'm going to give you another one in our next class probably. So this one I'm going to call it the first P test. Okay. Now I'm just going to generalize what we already proved here to any. I'm going to extend it to any real number here, no matter what is the lower bound of your integral here. Okay, we just prove it when we integrate from 1 to positive infinity. We're just going to generalize it for any positive number to positive infinity. So here I'm going to let let a, sorry, be a number which is greater than 0. And let p be any real number. So this means let p belonging to R. So mean p could be any number. Okay. In this case, the improper integral all right, so the improper integral given by integral from A is right here to positive infinity of 1 over x to the power p dx. You guys can see it's exactly the same integral that we prove here, except instead of a, we have our a equal to 1. And we just extend for all a. As soon as a is positive, the result is so this integral is convergent convergent. We already know the definition of convergent means if you calculate it, it's going to be a real number. So such integral is convergent if p is greater or equal to 1. And it's divergent if p is less than 1. And the proof is right here, you guys, here, as I told you. Oh, greater than 1, I did right here, is less or equal to 1. I'm going to remove this. Careful, it's just greater than 1, not equal. Oops. And this is, what we call the first P test, and we're going to apply it, in our next class in order to be able to conclude about very complex integral. Okay, just keep in mind when you guys have such integral, no matter what is your a, as soon as it's a positive number, this integral is always convergent if your p, the exponent of x, is a number greater than 1. Otherwise, the integral is going to be divergent. It means when you calculate it, you will get infinity. And based on that, I'm going to just give you a couple of integrals, and you guys can tell me which one is convergent and or divergent. All right. First example, you guys tell me integral from 2 to positive infinity of 1 over so in this case, this integral, is it convergent or divergent? We don't need to calculate it. It's quite easy to calculate, but we just want to know based on the p-test, is this interval convergent or divergent? So what do you guys think? So we have 1 over x to the power 3 by 2. Four by 3, sorry. So what do you guys think? Is it convergent or divergent?
Convergent.
Convergent because the p equal to 4 by 3. So we have this condition satisfied here. P equal to 4 by 3 and it's greater than 1. So it means when you calculate this, you will get a number, a real number. That's the reason. All right, those example. Think about this one. Is it convergent or divergent?
Divergent.
Divergent, because what is the value of p in this case?
1 over 2.
Exactly. Thank you. It's going to be integral from 5 to 8. 1 over x to the power half. So in this case, you know, p 1 over 2. And it means you have the situation here. I'm going to give so in this case, p equal to 1 over 2. And it's less than 1. And based on the p-test, it's going to be divergent. So one more example. Now we integrate say from 1 to infinity again. So we have 1 over okay. In this case, what's gonna be
Divergent.
is it divergent or convergent? This is 5, x to the power 5.
Convergent.
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 Exactly, because this is equal to integral from 1. So 1 over x of 5 So the whole thing to the power 1/3, right? And when you drop the brackets, it becomes integral from 1 to positive infinity, 1 over x to the power 5/3. Okay, so here in this case, it's going to be convergent because p is greater than 1. P here is equal to 5/3. In this case, p equal to 5/3. And it's greater than 1. Okay, guys, you guys can see here, you know, if the integral is convergent or equal to infinity without doing any calculations. So basically, it means you need to do the calculation if, for example, the question asks you to find the value of that integral.
Sir, I have a question.
Yeah.
So isn't cube root supposed to be 3/2?
Pardon?
Isn't cube root supposed to be 3/2?
No, it's going to be 1/3.
Okay, so if there was like 4 instead of 3, so it was 1/4, it would
Yeah.
be? All right, thank you.
You're welcome. If you guys have this, and n, no matter what is n, this is just equal to x 1/n. And that's exactly what you see. For example, number 2, you see? Because this means square root, it means here is the n equal to 2. Okay? So when the n equal to 2, we don't write it. Otherwise, we have always to write the value. If it is 3 or 4 or something else. Sounds good? Just keep in mind the p-test here, this theorem, and you guys can see, you know, help us to conclude about these integrals. All right, so next we're going to see the second type of improper integral. Can I erase this? Can I erase this? Or are you still writing, taking the notes?
Yes, sir, you can raise it.
Okay, thank you. So next we'll see the second type of integral, of improper integral. As I told you at the beginning of the lecture, I told you guys have 2 types of improper integral. And the first one is when the interval of integration is infinite. And this happens if at least one of the bound is either equal to infinity or negative infinity. Okay, and that's what we did, you know, before. Now, for the second type of improper integral, the bounds of your integral are both real numbers. But it's improper integral because of the discontinuity at some point inside of your interval of integration. It could be in the interior of the interval, or could be at the end point of your interval. And we'll see, you know, the 3 possible cases. So the first case is, you know, we have the discontinuity at B. The function is continuous everywhere inside this interval AB except at B. In this case, because of the discontinuity, we're going to remove the B and replace it by a parameter T and let T approaching to B from the left. Why? because we're integrating from A to B. And as you can see in this interval, it means A is less than B. So we have this situation here when we just want to make a picture. You guys can see A is here, and right here we have B, and we pick somewhere here, and we let T now approaching. So just be careful, T has no value. We just let T approaching to A, approaching to B, sorry. And as you can see, when T is approaching to B, it's approaching to B coming from the left. That's why we need the left hand limit. Okay. And as I mentioned now for the previous one, it's going to be similar. You calculate this integral in terms of T. When you get your integral in terms of T, now you let T approaching to B from the left. And in the second situation now, the discontinuity is not at B. Now it's at A, the smallest end point of your interval. And the technique going to be similar. You remove the point where, you know, the discontinuity is, and then you replace it by the parameter T. And this time you're going to let your T approaching to A plus. And you guys can see from my picture here, for the same T here, when you let your T approaching to right, your T is going from the right here. That's why we have to take the right hand limit. And the last possible situation is the function is continuous everywhere inside in this interval except at a point C, which is somewhere in between A and B. That's what I mentioned here. C is not equal to A, it's not equal to B, but it is somewhere between A and B. In this case, again, you have to split your integral into integrals. You're going to integrate from A to C, and after that from C to B. And you will get two improper integrals because at C, the function is discontinuous. And in this case, the first integral is going to be exactly, you know, what we got for the first situation here. And the second integral is exactly similar to what we have in the second situation. And you apply the same thing. So next, I'm just going to do some examples. All right, first example here. We just want to calculate the integral from 2 to 5 of 1 over x minus 2. And to calculate this integral, you guys can see the bounds of your integrals are both real, but it's still equal to an improper integral because at 2, at the lowest end point here at 2, my function is undefined. As you can see, when you substitute your x by 2, your function becomes 1 over 0 undefined. And if the function is undefined at 2, for sure, it's going to be discontinuous at 2. That's why we have improper. And for this example, what we have to do is to remove 2. So we have to calculate the limit of integral from to 5 of 1 over x minus 2, right? And so we let T approaching to 2, but T is approaching to 2 from the left or from the right?
Right.
Exactly. Because we're integrating from 2 to 5. And your T is here. And T is moving. T is going to 2. It's approaching to 2, coming from the right. So that's why I have to calculate the limit, the right hand limit. So now we'll get here the limits So when t is approaching to 2, and we know this is an easy integral, we can, what's the antiderivative going to be? What is the antiderivative? 1 over x minus 2. It's going to be ln of absolute value of x minus 2. And we take it at t and at 5. So the limit going to be, so we have to express, this function in terms of t before calculating the limit, because we calculate the limit when t is going to 2 from the right. So we'll get here ln of, you start to here x, when x equal to 5, going to be 5 minus 2, we'll get ln of 3 minus ln of absolute value of t minus 2. And when t is going to infinity, so when t is going to infinity, so we'll get ln of 3 minus, what's going to be the limit here? When t is approaching to 2 from the right. So the absolute value is approaching to 0 from the right. And the log function, when we're approaching to 0 from the right, is equal to, what is the value of this limit? When we're approaching to 0 from the right, for the log function,
That's 1.
this is a log function, and here is 0. What's going to be the limit when we're approaching to 0?
1.
1.
Now, the log is equal to 1 at e. I'm not saying ln of e, I'm saying ln of 0 from the right. You guys can see the picture here. What's going to happen when your x is here?
So ln 0 is in.
Is it infinity? Which infinity? Positive, negative?
It should be positive.
Look at your curve. When your x is really close to 0 on the right,
Sorry. Yeah, my bad.
it's going to be here, going to minus infinity.
Minus infinity, yeah.
And the answer going to be, what's going to be the answer? Ln of 3 minus infinity
Infinity.
is going to be positive infinity. And in this case, the integral is convergent or divergent?
Divergent.
Divergent, because the integral now is equal to infinity, as I told you. Anytime your integral is equal to infinity, which is not a number, it means the integral is divergent. To be convergent, the value of the integral should be a real number. So we can conclude here the integral, I'm talking about this integral,
So I had a question.
yeah.
So just as the integral says from like 2 to 5, and then you chose limit is equal t is equals to 2, are we always choosing the lower bound and then replace with another alphabet as a constant? Or we can also take the upper bound and also replace it with as a constant?
Okay, listen to me. I'm gonna tell you again. I told you at the beginning of the class, we have two types of improper integral. Okay, the first one is when one of the bounds is infinity. And that's what we did before. And the second type integral, improper integral, is when the function that you want to integrate is not continuous at a point. And I told you, you have to remove that point. It's not just like, of the point, no. And I repeated here the reason why we remove 2, because I said when you substitute x by 2, your function 1 over x minus 2 gonna be undefined. At 5, your function is defined and it's continuous. But at 2, it's gonna be undefined because you will get 1 over 0. And when your function is undefined, it's gonna be for sure discontinuous. It's improper integral because the continuity is missing at 2. That's the reason. You getting me? Hello?
Yes, sir.
Instead of 5, at 2, the function is not continuous. And anytime your function is not continuous, it means at that point, so you have to remove it and replace it by t. It's not just picking one of them, whatever you want. No.
Got it.
That's exactly what I told you for these 3 situations. You see, I said f is continuous except at b for the second case, the first case. And for the second case, I said it's continuous in this interval except at a. And for the third case, I said it's continuous except at c, where c is a number between a and b. It's related to the concept of continuity. If you don't have the continuity, it means your integral is not a definite integral. It becomes now an improper integral. That's a difference between the 2 types of integrals. For definite integral, you have the continuity, and you just apply exactly what we did before in the previous chapters. And for this one, because of the discontinuity, it means the continuity is missing. So that's why you have to apply exactly the limit here. Okay? Now the improper integral is divergent because we have infinity as its value. Now be careful, if you just remove the 5, when comes time to calculate the limit, you will get here 2 minus 2 going to be ln of 0. And we're not calculate, we can calculate ln of 0 because it's undefined at 0. What we calculate is not ln of 0. We calculate here the limit when the absolute value here is approaching to 0. It's different to f. I'm saying limit is approaching to. Any question? All right. Can I erase this? Second example. Now we want to integrate from 1 to 4, 1 over root of x minus 1. in this case, you guys can tell me the point where the function is not continuous.
1.
At 1. Okay, so be careful. All right, sometimes the point is, not the endpoint. It could be somewhere inside, and you have to double check that the domain of your function. You see, at 1, the function here is undefined, because when you substitute x by 1, it becomes 1/0, undefined. That's why we have to remove. This is the point that we need to remove. Okay, now in this example here, so we're done with that one. All right, for this example, as your friend said, we have the discontinuity at 1. That's why we're going to remove 1 and replace it by t. And then we let t very close to 1, coming from the right, similar to the previous example, because your t is between 1 and 5. And when it's approaching to 1, it's going to be from the right. Now, so we calculate this integral. The antiderivative going to be 2 root of x minus 1, because I realize here this function has the form of 1 over 2 root f. We have exactly these forms: integral of 1 over 2 root f times f dash. And we know this is just equal to root f based on the chain rule. When you take the reverse way, it's going to be your chain rule if you're going from right to left. And that's exactly what I observe here. My f is equal to x minus 1, and is f dash going to be just 1. But the 2 is missing, so that's why I multiply by 2. But if you don't realize that you guys have this form, another way to calculate integral is to use the substitution rule. It's going to be a little bit longer, but you can do it if you want to. You can use the substitution rule by setting u equal minus 1, and your dx going to be du. You change the bounds of your integral as you already we already did. Okay, now since it's going to be a little bit longer, but I realize I have exactly this form. So it means if you know your derivative formulas, you're going to save time. And calculate it at 4. When you substitute x by 4, here is going to be root of 4 minus 1, going to be 2 root 3. And you substitute now your x by, get the second term. And you let your t approaching to 1 from the right. And in this case, this is a constant, does not depend on t. And the second one, when you substitute t by 1, it becomes 0. And the solution is going to be just root 3. And you guys can see here in the first example, the improper integral is divergent because it's a value equal to positive infinity. In this integral here, in the second one, the integral you can see equal to a real number. So it means this integral is convergent. Any question?
So can you write the formula, please?
Which formula? Are you talking about this on the right of my screen?
So I'm talking about the like the integration, like you did the integration, that formula. Like
Here?
yeah.
Is
Yes,
here, is
this
this is here? It's right here. In this case, my f in this example, f equal to oh, sorry, it's equal to x. So in this case, you know, f equal to x minus 1. And the f dash gonna be 1.
Oh, okay. Thank you, sir.
You're welcome. And the other way to do it is that you can use, if it's going to be just a little bit longer, you can use substitution by setting u equal to x minus 1. And you will get the same solution. Is it okay? Any question? All right, so if there is no question, I'm gonna let you go. We have 4 more minutes. I'm just gonna leave it here and take the attendance. Okay, I saw in the chat somebody's asking if there is a class tomorrow. I don't know, because I double check, you know, in the portal, but that just said, you know, they didn't say if there is a class or not. I'm gonna double check and just email you by tomorrow if I get anything. Or what they said is just, you know, if you guys go to the student portal, they mention here the ICM virtual services and offices will be closed on November 11, but they didn't say anything about the courses. So I have to double check the course online or ask it to some people if there is something new. And I'll let you know by, okay, advising course for Remembrance Day, advising courses. Okay, I didn't see anything here. Okay, I'll double check and we'll let you know by tomorrow. So did you ask to your the instructors? No?
The other one said there's no class tomorrow.
Or that's what the told you?
Yeah.
Okay, so I have to double check and I'm gonna talk to someone and after I'm gonna let you know. I'm gonna just email you about it, okay? Thank you. Mangabet, you still here? Mangabet, I saw you before. Mangabet, are you here? Gone? Fatima? Fatima Bukar, are you here?
Yeah.
All right, thank you. Al-Amin? Al-Amin, are you here? No? Thank you, Bao.
Yes, I'm here.
Thank you. Kong Ho.
Yes, sir. I'm here.
Thank you. Zi Kiang. Oh, sorry. Abdullah Al Mamun.
Yes, sir, I'm here.
Thank you. Zi Kiang Fang.
Yes, sir.
Thank you. Ali Abdullah Fardin. Ali, are you here? No. Shams Al Fardin. Shams, are you here? No. Mustafa Faisal.
Yes, sir.
Thank you. Fernando, you here?
Yes, sir.
Thank you. Pusha.
Yes,
Is
sir.
she- All right, thank you. Omam Hassan. Omam, are you here? Omam Hassan. Muhammad Oman Asim. No. Cedric Iradukunda.
Yes, sir. Yes, sir.
All right, thank you. Samar Kapil. Samar Kapil, you're not here. Abdul Mushan. Abdul. No. Yunwan Kim.
Present.
Thank you. Chow Min Tai.
I'm here, sir.
Thank you. And Shuo Liu. And Shuo Liu. Liu.
Yes, sir, I'm here.
All right, thank you. Kandap Malani. Kandap, are you here? Not here. Vasily, I saw you before. Are you still here? Vasily Mironov.
Yeah, I'm here.
All right, thank you. Saida Maria Janat. Maria Janat Mukhar. No. Shamil Munashipov.
Yes, sir.
Thank you. Tengis.
Present.
Thank you. Marco. Tikfeng Marco.
Yes, sir.
Thank you. Jakwan Park.
Yes, sir.
Thank you. Jayton Patel.
Present, sir.
Mai Patel. Mai Patel.
Yeah.
Thank you. Subkumar Patel. Subkumar Patel, are you here? No. Azikuzaman Rifat. Azikuzaman, are you here? Christopher.
Yeah.
Thank you. Navid Hassan.
Present, sir.
Thank you. Midhan Shushipal. Midhan Shishupal. Not here. Yeah. Mangabet. Yeah, I call you. I thought I saw you before, but I called you. I said, are you here? Okay, let me double check after. Ali Muhammad Mahmoud Usman.
Yeah.
All right, thank you.
Yes, sir.
Thank you. Zi Cheng Yi.
Yes, sir. I'm here.
Thank you. Yi Ken Zhang. Yi Ken Zhang. All right, that's all for today. Thank you guys. And